Nah,
Technical
he
test?
nothing. I
Nothing?
said, hey, can you send me a exam so that then I can
Oh,
review
okay.
it with y'all? And he's like, sure. Their exam's on Friday. I'm like, cool. And so
And then,
that was it.
oh, and that was it?
Yeah.
Oh, wow. Okay.
But to be fair, I don't ask him that many questions.
Yeah. No, it's okay. I thought he might have said something like, "Oh yeah, like these are the type of topics or whatever." But I guess
Yeah,
he's
I
really
I heard that he might not do problem 3 because like this goes a bit more into different types of op amps, and I heard that you'll haven't touched the materials for
the filters. Yeah,
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 all the different types of op amp um like
yeah. It's mainly
lock and key or
gains.
something.
Yeah, it's mainly gains and bandwidth.
Mainly gains. Okay.
Yeah, for the
Um
gains and bandwidth. So like if there's anything that relates to gains and bandwidth,
this one's
um,
the gain.
then yeah, then it's most likely going to be. But that one was exactly on the homework. But
Oh, that's
we
true.
would like to see how you do it
Sorry.
though. Maybe your way of method might make a difference though. Because like when I did it, I'm
Hmm.
not sure if I did it right, but the numbers were like around like something realistic.
That's fair. I'll make sure I can cover as in depth as possible.
Okay.
Um I guess since it's maybe relevant, I'll start with problem 1 first, and then I'll go to problem 3.
Okay.
Okay. Let me bring the problem in here. This is such a cool feature. I love this feature so much. It saves you so much time.
Oh, like are you on an iPad or something?
No, I mean that if you're on Windows 10 and you search snip,
Oh yeah,
it'll
yeah,
pull
yeah.
up this
Yeah, I
so
use that.
wonderful.
Yeah, no, that's a nice feature. On the MacBook, you just do like I think Alt Shift 4, and then you just kind of create that space, and then you copy it. It's the same thing too, but it just has its own command.
That's awesome. There's probably a command on here, but like I'll look it up later and
Yeah.
then see how that goes. So for this problem, we're going to be looking for we're given mu for 5,000. We're given input impedance is infinity and output impedance is, or not impedance, but resistance is 0. And then the open loop frequency is going to be 100 hertz. So it says where GVDM is the open loop differential mode voltage gain. Oh, yeah, yeah. And then I explain FOL. Use these model and the loop gain method discussed in class to calculate values for the parameters. Listen to table 1 where G epsilon is the gain error and FCL is the closed loop bandwidth in hertz for the voltage driven configuration and then the current driven configuration. Compare the results and indicate which configuration produces the better performance. Okay, so then for this problem, what we're going to start with is we're going to convert the amplifier to, I believe, this small signal model. Or for since it's a voltage-driven amplifier, we're going to convert it to its voltage form. So we have our source, and it's going to be a resistor. We got another resistor, and one more for good measure. and then a resistor to ground. Then we got another resistor coming up here. Then goes around to one last resistor. Got the output voltage, and then since it's a voltage driven, that means you're going to have a voltage source here called Vn. Oh, sorry, not Vn, that's Vm. And then that's linked to ground. So the way that this works is that for this voltage-driven amplifier, we're going to want to calculate the feedback function f. F equals change in V over Vm. Now, for this to calculate feedback, what we do is we set our voltage source, or our voltage-driven voltage source, equal to 0. So now it's saying the difference between this point and this point are 0. So we know that current equals voltage over resistance. So since it's 0 over R, that means there's zero current, meaning there's nothing flowing through here. So we can pretty much cut this part off. Or, right. Oh no, that's true. 1 second. No, sorry, because the voltage is 0, that means that it's going to be closed. I forgot that there's a voltage difference. This isn't a voltage. Sorry, let me select. Let me erase that. That's actually. So what this is actually saying is whenever you say, this kind of goes back to that first part, is that whenever it says that this is, whenever you connect 0 volts to this, you're saying that this is 0 and that this is 0, or you're saying that they are the same points. And so just like a straight line, where if this is a volt, if this is like 5 volts, and then this is 5 volts, and then this is 5 volts, any place minus the other place is still 0, and therefore it's a short. That's why whenever we set this voltage right here to 0, let me get rid of kind of the messiness of that.
Basically, you're saying when it's voltage driven, that means that your source is going to be equal to 0?
Yes, because you're going to be finding feedback.
Okay.
And so since it's 0 volts at since it is saying that this place right here minus this place right here, since it's 0, then that means that there's no voltage drop. And since there's no voltage drop across this line, that means that that this resistor disappears.
Yeah, pretty much. It's because current will take the path with the least resistance.
Oh yeah, it'll just go straight through the source rather than
Right.
the resistor.
Pretty much. Yeah,
Because
so
the yep.
least resistance. Yeah. I just think of it like water flow.
Oh yeah.
Kind of funny, but that's just kind of how it works.
Honestly, everything works out to water every single time.
Yeah.
I have not found a place where water is not a good analogy for electrons, because it's just either a flow of H2O or it's a flow of electrons. So then we have the 7K resistor disappeared, and then we have the 1K left. We got the 2K. and we got the 3K, and we got the 4K. So now, change in V is going to be right here. And the reason why that it's going to be negative, positive, and the reason why is that from the op amp, those are the two connections that this right here is change in V, where that's negative and then this is positive. So that's kind of what we're measuring, the change in difference between. There we go. So then what that looks like is that then we're going to do KVL to find change in V. So we start with, oh, there's the mouse. So we see it's positive here. So then we're going to flow, let's flow counterclockwise. Actually, let's not do KVL, sorry. We're going to do voltage divider because what we can do is, since this becomes just a straight line, now these two resistors are in series. And so then we can add them in series. So that's going to look like resistor, resistor, another resistor down here, connects to ground. Our voltage source, VM, or his writing's really weird. I can't tell if it's VM or VN by this point, but it is VM. It is VM. So change in V divided by VM, and then this right here is also VM. And then this leads to your output right here. And then you got a resistor right here. So now effectively you have three resistors where this is your 4K. This is now 1 plus 2, which is our 3K. And then we got our 3K. So now we have F, or let's go with change in V. Let's do change in V is equal to our voltage, what's generating the voltage, our independent source, times the voltage divider. So that's going to be we're going to see change in V right here. So VM times 3K over 3K plus 4K plus another 3K. So far, so good.
Yeah.
And then since we're looking for a change in V over VM, we're going to divide both sides by VM. And then that is going to cancel out your VMs. So VMs go away and you got your F. So F is going to equal 3 over 9 plus, or sorry, not 9. It's going to equal 3 over 3 plus 4 plus 3. So it's going to be 10, or 3 over 10. 3K. Mouse is really bad for drawing, not going to lie. Over 10K. So then the K's are going to cancel out, and that's going to get you a frequency of 0.3 hertz. So from there, oh wait, he's using F in a different way. So this isn't frequency. This is a feedback function. So it's not actually hertz. But from here, once we have that, we use the return difference equation, which is going to be F equals 1 plus T. And then your T is going to be mu times your feedback function. 1 plus mu F. And then we can just pull those values from here. So it's going to be 1 plus 0. Let me do this in order, times the number over here. If I can find my mouse again. 5,000 volts. Times your 0.3. And then from there, we can multiply that out, and we get 5,000 times 0.3 equals 1,500 plus 1. So we're going to get your return function is going to equal 1,501. That's very bad looking. 1,501. There we go. And so from there, our G epsilon equals negative 100 over 1 plus UF, which is our feedback function. So it's going to be negative 100 over F. This is also going to be times 100%. Which is going to equal, let's see, negative 100 over 1,501. So 100 divided by 1,501 is going to be 0.0666. So it's going to be negative 6.662%. That's not lining up with what he's saying. 1 second. So 100 over 1,501. I think this may have been his problem. 100 by 1,501 equals 0.0666. In his answer, he says 0.0666%. I think this is actually an error on his part.
Oh, let me see. Let me check as well.
Which I've seen that like I've seen that a few times, but like for problem 3, no, this is problem 1, sorry. Problem 1, let's see. I think he's getting a different value for 1 plus UF.
What did he get?
So,
what did he get for the gain here?
oh, okay, I think I'm... Oh, okay, I was looking at different... Oh, wait, never mind. 1 second. Sorry. This is all... Okay, yeah, so he did say negative 100 over 1,501%. I mistook that the 100 on the top is actually him doing the multiplication of 100. So this 100 that I wrote was actually my fault. I saw the percentage and then I was like, oh, okay, multiply by 100%. But no, the 100 in the numerator is him making it 100%.
Oh, okay, so it's supposed to be negative 1 over 1 plus mu f?
Yeah, so it's like, let me get rid of this. It's going to be negative 1 over 1 plus UF times 100%. So your G epsilon, does it say the exact name for what okay, your gain error, that's what he's using. So your gain error is -1 over 1 plus mu f. But he wants it in percentage form, and so that's where the 100% comes from. And that's going to get you 0.0662%. And then from there, he says 6663%. So there we go. And then for the closed loop, it's going to be f of the closed loop is going to equal 1 plus mu f in parentheses times f of the open loop. And so we're given f of the open loop, and we know our f value, so that's just going to be 1501 times 100 hertz. And that's going to equal 150,100. Or 150.1 kilohertz.
I have a quick question.
Yes.
So earlier when you were doing your return functions,
Mm-hmm.
it seems like there's two capital F in the same equation. You know how like
Oh,
what's
you're right.
yeah,
Yep.
so what's the symbol for return function? Is that a beta, right? Or is it
So let me erase this real quick. So honestly, this is the first time I'm hearing of a return function. This is a two-port network thing that is probably going to be more of a PhD thing. Oh, my computer froze for a second. Okay, there we go. I think it's back. So like you'll learn about control system in control systems. There's much more about gain error and how to find those things about either your gain error or if you put in an input, what is your output going to look like? For this, a lot of the things such as open loop frequency, closed loop frequency, and then the gain error. I mean, not gain error. Sorry. Return difference. That definitely sounds like much more upper level terms that you won't hear until like you go into your master's or PhD. I feel like, because I haven't encountered them yet for
okay.
for return difference at least.
Yeah, no, yeah, but Dr. Russell, the way he talks is just he's so at that level that it's normal to
Oh
him.
yeah, he like I believe he ran quite a few of his own businesses in the silicon industry, and so like he knows a lot about it. He
Yeah,
teaches for fun. That's like this is his pastime, is teaching
yeah,
circuits at UTA.
yeah. Okay, but no, it makes sense.
Um, for part B, let me unzoom out of this. For part B, we're going to want our voltage driven. Let me just add this here. So he does want it in percent, so I'm going to do 0.06663%. And then we're going to put our 150.1 kilohertz. And then now we're going to do current driven. So we're going to plug in a current source. So since voltage source ends up being a closed or short circuit. Since it ends up being a short circuit, placing in a current source, that's going to be a open circuit. So now we include the 7K. And so that just modifies our voltage divider. So like for instance, let me change this part right here. So now this part right here turns into, you have that resistor back, you have your current source. So with this, you're going to set the current to 0 for feedback. And so since the current is 0, that means nothing is moving through this line. Therefore, its only path is to go for a resistor or go through the resistor. Previously, since the voltage was 0 along here, it was saying that since there is no voltage drop, it was a straight line before. So now that it's going to be a current source, now it's going to be an open. So no connection for here, and you're going to get that resistor back. The resistor is going to be included into the voltage divider equation. So you got your 7K in there. And then from there, we go back to do the same method of F equals change in V over VM. And so then that's going to get you F, or let's do change in V. Let's do change in V equals that whole voltage divider of your original voltage source times these 3 resistors added together, because that's going to get you your change in V across this series of resistance. So that's going to be your 7K plus your 2K plus your 1K divided by those 3 added together, which would be 7, 10. That would be 10K plus 4K and plus your 3K. So now that you got those down, now you just got to divide both sides by VM, and so F just ends up being 10 over 17K.
Wait,
Or
could you
10, yes.
explain real quick like how you derive that
Yep, I can. Absolutely.
resistance? Like, is it because it's changing directions then? Like, it's going from the positive of delta V up
So
past 75?
focusing on this one, it's the same circuit, except this is now open. So
Right.
that means this circuit has essentially turned into, let me select this. So essentially, it's now like this. This is now the new circuit.
Yeah.
So before, it was closed, meaning that all the electrons went through the straight line instead of the resistor. And at this point, we're saying, okay, none of the electrons are going through the source. They're just going through the resistor. And so the way that works now is that this right here, this is all added together. Like you have 3 resistors in series, and you can add all 3 of those resistors up. And whenever you add those 3 resistors together, you get a brand new resistor that's right here. That's going to be your 10K.
Okay.
And so now, yeah,
and so your delta V would be then VM times 3K plus 10K over 10K plus 4K.
it's going to be the 10K over the 10K plus the 4K plus the 3K. Because that'd be your voltage divider, is the one that you want over the ones that you don't, over everything. It's going to be the ones you want over everything. So when you, let's see, So just the same way for the previous F, the way that we got the previous F, we did a voltage divider of where we excluded the resistor when adding up the two resistances. And so this time the only difference is that we're now including the 7K in our calculation, and then that 7K is just part it's now 3 resistors in series instead of 2 resistors in series. And so then you're just able to add those 3 resistors together to get a 10K.
Right. And so yeah, and so when you derive for delta V, you would have Vm times 10K, and then over the total of everything else, like 3 plus 4 plus 10K.
Yes.
Okay.
10K plus or minus plus change in V. So now that's just gonna look like just what you said, was that the F is equal to the, or sorry, yeah. I can do Vm times your 10K over 10K plus 4K plus 3K. And then since F is change in V over Vm, we divide it all by Vm. Because this top part, this top part right here is equal to change in V. Does that kind of make sense?
Yeah, that makes sense.
Cool. So then from here, we notice that the VMs cancel out, and then we can just figure out what the fraction's value is. So that's going to be 10 over 10 plus 4 plus 3, and that's going to be 10 over 17, and that's going to get you 0.5882. And now that we have your value for F, we can calculate the forward function. Is it forward function or difference function? I think it's difference function is what they called it. Return difference. The return difference F
Yeah, return difference.
equals 1 plus mu F. Oh, I did it again. F. And that's going to be 1 plus 5,000 times 0.5882. So when we multiply that out, times 5,000 plus 1, that's going to get 2942. So F equals 2942.17. And so then from our G error, or our gain error, we're going to get, it's going to be -1 over F, just like the previous equation. It was the 1 plus mu F. And so I'm just simplifying it down to F equals 1 plus mu F. So we can just change it. And then from there, we can multiply it times 100%. So now we have it in percentage form. So doing 1 over 2942.17, 1 divided by 2942.17, that gets us 0.000333989, or negative. And then we multiply it by 100. So that's going to get us negative 0.03. Let me make this period a bit bigger. 0.3399%. And then from there, we saw that our closed loop frequency was just 1 plus UF times F open loop. So FCL is just really equal to our return difference times open loop, because we're just substituting in 1 plus UF. for F open loop. And then that's 100 times 2942. 294,217. And then that's just equal to 294.22 hertz or kilohertz. So like this one up here is just hertz. And then I just made it kilohertz by dividing it by 1,000. So far, so good?
Yeah.
Then I'm going to move on to the third problem. Because, oh wait, let me make sure that that was the whole question. Because like, even though we circled the values, explain in detail, compare the results and indicate which configuration is better. So 294.17, or sorry, point 22. 294 kilohertz. And then a gain of, oh wait, I forgot to include the negative sign up here. Negative 0.0339%.
I think so. The last question is to indicate which one produces a better performance and explain why.
Yes. And so which one do you think would be better?
I think the voltage driven because the bandwidth is lower and the percent error is lower.
So we actually want the higher bandwidth, or mainly also the gain error. So since, so what you can think of as gain error is that whenever you are trying to figure out, you want to be as precise as possible with whatever you're doing, right?
Right.
So less error is technically better. So that's kind of the first. What he says, or what he states, is that the current-driven amplifier outperforms the voltage-driven configuration, since its gain error is roughly half of that of the voltage-driven amplifier, and its closed-loop bandwidth is almost twice that of the voltage-driven amplifier. This, due to the larger loop gain T produced by the current-driven circuit.
Oh, okay. Oh, I thought I saw a 4. That's why. For
That's all
your
good.
yeah.
Sometimes, like, bandwidth, maybe that is, like, for instance, in telecommunications, having a high bandwidth would be not preferable. But in the standpoint of from like someone designing amplifiers, is that you don't know who's necessarily going to be the ones that are totally going to be buying your type of amplifier. And so having a larger bandwidth of signals that are allowed to be used with your amplifier is technically a good thing. Because then that wider range, maybe they are doing something in like, maybe they're dealing with signals in 280,000 kilohertz. But if they're using the voltage driven, then that's out of the range of their application. And so then that would not be a viable amplifier. And then they go off to some other person's amplifier. And now you just lost a customer. And so that's the kind of idea, is that for this intent, we want a bigger bandwidth because we want the operational amplifier to work for a lot more signals.
Okay. But mainly it's the gain error that you want to look at first, right? Because you want it to be stable and less of a difference for the feedback, like coming back.
That's true. Yeah, I think he specifically was mainly also focusing on gain error. I was just pointing out bandwidth because bandwidth seemed a bit more finicky of a thing. Like, how do you quantify which
Right.
bandwidth is better? Definitely look at the gain error, and whichever one has better gain error, that's probably better. But if like one's 150 kilohertz and then one's like 1 hertz, probably the answer is wrong. But but the but yeah, just
Yeah.
things to
But it's
consider when building op amps.
but it seems like the two the gain, error, and bandwidth are related anyway. So I think it's like every time you find either one, like you can always find both because the two are pretty related in terms of op amps um, type of.
Yeah, I know that I'm working on like one project right now that like the whole entire gain function is entirely related to all the frequency of all the switches switching on and off. So definitely they do have a lot of relationships between the two. Let me switch over to the third problem.
Okay.
If you feel pretty good about this problem.
Yeah, I feel pretty good.
Cool, cool. Then let me load up that problem. Application problem. The op-amp circuit shown in figure 3 is the topology of another version of the multiple feedback bandpass active RC filter. The op-amp is assumed to be ideal. Apply the analysis equation developed in the SAB handout to calculate values for the biquad parameters omega p. And so I know that y'all aren't going to have the analysis equations. So I'm probably just going to run through this and try to explain to the best of my ability what's going on. And then hopefully whenever that's brought up later and he might bring up a test about that, then anyone who's looking at this can refer to it.
Okay.
So let me snip gut this. Copy that. So from the handout, in this case, from the notes, what you're going to have is you're going to have a equation given about what is the gain for this specific filter going to look like. And so in this case, the voltage gain in the S domain is going to look like. Has he ever talked about S domain? I mean, this circuits too. Yeah, he's touched S domain. Yeah. Just making.
Yeah,
Sorry,
that's
I'm just making sure that I was like, wait. I was just dealing with some circuits 1 people, and I was like, wait a minute, he hasn't touched that for them yet, and I was like, wait.
yeah, it's
Yeah.
just in the form of Laplace transform.
Awesome, awesome. So pretty much what you're doing here is you're going to take each resistor and capacitor and turn it into it's either going to be an admittance or it's going to be an impedance, depending on the equation. In this, at this point, it's going to be or for this, I guess, topology, the gain equation given is going to be in admittances. Y3 of S. Actually, maybe I should just get rid of the S's because I mean, like, it's going to be in S's. Everything's going to be in S. Or it's going to be in terms of S, and it'll be a lot less writing for a mouse to do. Y3 times Y4 plus Y5 times Y1 plus Y2 plus Y3 plus Y4. And so this is pretty realistic, at least in terms of like whenever doing a control system that like you'll have different types of feedback incorporated into your designs. And so those are going to have those are going to form different gain equations. And what you're going to want to find is the first you're going to want to find out what order is your equation. Is it first order, second order, or third order? And then usually there's an equation relating these parameters right here. And so I'll be able to show you what those parameters are, or what the typical equation is going to turn into. For this, we're going to turn y1 is going to equal r1 over r1. y2 is going to equal 0. Okay, so they're in. One important thing is that you have to compare the circuits in the notes to the circuit that you're given. Because for instance here, whatever y1 was, or whatever y2 was, it just was not here. And so probably what that means is that it was just a straight line, maybe here, maybe this was supposed to be the y2, or maybe this right here was supposed to be y2, and so nothing's there, so there is no resistance. Or wait, no, that would be completely wrong, because y2 equaling 0 is saying that some resistance, 1 over something, some resistance or impedance. If we were to solve for this, R is going to be equal to infinity. And so if the resistance is infinity, then that means that it's an open. So that means maybe there was something connecting the two, or maybe there was something over here that went off as a resistor and then connected to ground. And then because it was not there in the circuit, y2 is equal to 0 because the impedance for that would have been enough to completely make that part an open in the circuit. And so that's why y2 is probably equal to 0, or why it said that y2 is equal to 0.
Why would you what makes you like assume that like R2 would be like right there instead of like others?
Well, because one, I don't have the handbook in front of me right now.
Yeah.
I have the solutions, but I don't have the handbook. So like he's going to give out notes, and from those notes, you're going to be given a circuit that looks like a bunch of like this is going to be Z1, and then this is going to be connected to some other piece that maybe this is Z2, and then you have this leads into some op amp like this, and then maybe this is Z3 or something that leads off to ground or something, and then you have an output, and then that's linked, and then this has Z4. You're going to get a schematic of what the basic topology of the circuit's going to look like, and then you're going to have to determine is Z1 capacitor 4, or is Z1 if I had a resistor right here that like connected right here, and now you have a resistor and capacitor 4 in parallel, then you have to combine the two into one straight line, and then that would be your Z1. And so it's pretty much taking topologies from your notes and then trying to make your circuit fit the best topology for it. And then you're able to calculate your gain function. And then that's the kind of idea behind the filters, is that it's going to be complicated circuits that are going to fit certain already, some company has already gone through all the calculations for what the gain function would look like. It's just your job to go in and implement or show how this circuit is the same as that circuit from the notes, and then find the gain function for it. But then from here, your y3 is going to equal. Oh, okay, yeah. So this is just like what I was talking about, is that you have R3 in parallel with C3, or it adds R3 and SC3 in parallel for some reason. Oh, wait, okay, no, it adds them in series, but then it takes the admittance of that value. That's what's happening. So it's going to be 1 over R3 plus 1 over SC3, because R3 plus 1 over SC3 would be the Z3 value. And then Y3 is your 1 over your Z3 value. And then, let me erase this. We're going to get our Y4 value equals SC4. And then our Y5 value is going to be equal to 1 over R5. And then from there, you plug that into the equation. What's he trying to do here? Okay, so here he loves his algebra, so he goes through a whole algebraic definition of how you can simplify this whole thing without a calculator, which unfortunately I am not talented enough to do in the short amount of time of 1 hour and 20 minutes as I am given during a test. So enter these values into a calculator, and then once your calculator spits out an equation, it says checking through. Let's see. This is horrible. I'm so sorry. This is because what he does is he says that this equation is really equal to P of S, or negative P of S, over Q of S. And then P of S, whenever you multiply it out, equals G1 SC3 over SR3 C3 plus 1. And then your Q of S is a really long equation I'm not going through the derivation for. But it turns into the form C3 C4 times 1 plus G5 what is that? R3 divided by SR3 C3. He's using G's and R's. Like, that's why I don't do the algebra for this.
Yeah, it's just like, cause like what I would do, I would just put in like the values of like what's given to me, like the R and this resistance and the capacitance, and then just put it in terms of S. Would that work too?
honestly.
Yeah.
But then the main values he's wanting are oh, okay, I see what he's doing. Okay, so what he's essentially done is he's pretty much turned, so the general form for is this a second order? I think it's a second order. No, I can't tell. It only gets worse from here. This is really bad. I'm not gonna lie.
Do you think you can also upload the answers too in the chat? Or...
Yeah, I feel like that's what I'm gonna have to do for this, because like, yeah, let me pull up the answers on here, because there's so much derivation in this, and I mean, like, that's pretty much all that I've been doing, is just like showing how the answers come about. So let me pull that up. Let me stop sharing for a second, and then let me pull up that document so then you can see that. There we go. Okay, you see this?
Yes.
So you're going to have these notes from SAB notes for multiple feedback topologies. And then it's going to give you some gain equation like this. And then you're going to have to determine what is your Y1, or what are your your admittances for these values, and then you're going to plug that into your calculator. And then your calculator is going to give you for this, I believe, a second order equation. If it's not second order, then I mean it's definitely not going to be first order. I feel like it's going to be second order. Like anything that you plug into here is either going to be second order, or there's going to be a way that the handbook tells you how to calculate third order. Because there's a bunch of special things with second order that you can find omega p, qp. Pretty much here's a bunch of derivation of him saying you have P of S, which is the numerator, as you can see, y1, y3, y1, y3 in the numerator, and then Q of S, which is the entire denominator. And then he does a whole ton of multiplication, a whole bunch of combination, which is really long. Not something I think I should write on with a mouse. But going through all of this, he turns this into Q of S equals a okay, so this right here, focusing on this, how is he doing this? Okay, so from here, what he's doing is this is the denominator, and you can, he's essentially pulled out an S to make this a second order equation multiplied times, I guess, a first order equation. I don't like the way he does this, to be honest. I'm not for it. But the way he's done it is that he has omega p, he has qp, and then omega p is equal to this this polynomial in the numerator of S, and then qp is equal to this denominator. And then whenever he solves for that, hold up. Oh wait, never mind. Okay, so what he's doing is that omega p squared, this bottom right number, in order to find omega p squared is equal to the g1 g5 over c3 c4, that kind of thing. You just do the square root of that, and that gets you omega p. Because we do not know what qp is compared to omega p, so that's why he has to go for this right term first, squaring this term to equal omega p. That's how he gets omega p squared is equal to that term, and then he does square root right here. And then plugging in the values gets you an omega p, and it gets you a frequency. And then he starts off with the omega p up here. And then omega p over qp is equal to this whole thing. And he pretty much plugs in omega p, and then he solves for qp. And then solving for qp gets you a value of 2.5. And then the qp goes into your quality factor, and that goes all into your dampness, or your Yeah, your damp value, I forgot if it's like damper, but it's a really important fact. It's a really important number because a very high value means that it is going to be a lot less sinusoidal, while a very low value means that it's going to be very sinusoidal. But the importance of that is that if something is more sinusoidal, it's going to have a much quicker response. So if I like turn on, let's say that I have a device and I turn on that device and my output is it has like a 0.01 QP value, then that means that it's going to spike really high. And that means it's a really quick response, but it overshoots what I want. If I want like 48 volts, it's gonna, whenever I turn on that device, it's gonna give me like 70 volts. And then it's gonna try to stabilize back down, and maybe it'll like keep oscillating around 48 volts. And so that's what happens whenever you have a very low quality factor. But if you have a really, really high quality factor, then that means that the response is going to be really slow. It's going to slowly rise up. It's going to take a few seconds for it to get to the 48 volts, but the final 48 volts is going to be it's going to be much more straight. It's going to be a lot less sinusoidal. And so the question is, how do I balance the two? How do I make sure the response is quick enough that nothing blows up, but also not sinusoidal enough to where it also blows up? And so it's take whichever blow up you want. So that's the there's a whole bunch of design specifications I have to figure out for that. Um but from there he says P of S over Q of S gets you all of this. Um let's see. So this S cancels this S, so it's not first order. These are just okay, so this is a second order system. So the way that this works is that you take the numerators S's and you cancel them out with the bottom S's. So like to figure out what kind of order it is if I have an S cubed in the numerator and I have a S to the fourth power in the denominator, then that's a first order system because the S cubed in the numerator, no matter like how they're kind of multiplied out, the S cubed cancels out with the bottom one, kind of making 1 over S plus something. That's just kind of a way to think about it whenever you see this. So what he's doing here is you see an S in the numerator and you see an S in the bottom. If there was no S in the numerator, then this would be a third order system because this S would multiply with these other S's in the right-hand side. But since technically the top S and the bottom S cancel each other out, it's just a second order because there's a S squared term, and then that's the highest order that it gets is S squared. And then solving for those values, you get this large, yeah, circuits too. And then so your K value is this is the main equation that I want to show. The WP over QP times S over S squared plus. Now I'm confused, honestly, at this point. There's an S in the numerator, so now this is technically a first order equation. I believe this is all going to be in the handbook. It will give you these equations in the handbook because this is obviously a completely new topic that deals with different frequencies and quality factors or dampness factors that you're going to learn all about in probably after the midterm. But KBP is pretty much your gain. That's going to be that's going to be a value that it's the best way to describe it. I mean, obviously in this equation we see WP over QP, so it's going to be whatever this numerator is divided by omega P over QP, and then that'll be your KBP. But oftentimes you'll get a most oftenly you'll get a form of K times omega P squared, and then divided by this what's in the denominator. That's like a very often used form. You'll learn a bunch more about this in like control systems um later on. But there's a whole bunch of derivations for how all this goes down, and it's pretty standard stuff, so you'll kind of learn it later on. And so if it feels confusing right now, it's because it is confusing. I hope everyone's nodding their head with that because it is a bit confusing. And but just trust the system that the system will teach. Yeah, and then you'll get your KBP from dividing it out, and then you'll get KBP.
So KBP is the gain, and so what's GB again?
It's like a constant. So like, for instance, if I had, let's say I had a gain, like a voltage gain. So if I wanted to, my input was 12 volts and it outputs 48 volts, then that's a gain of 4. But
Oh,
let's
okay.
say yeah.
No, that makes sense.
Okay.
Yeah, keep.
But let's say that like I introduce some other component into the circuit that somehow changes the S values or whatever. And my main point is, let's see. It more of just it's a multiplier. Like for instance, if like KBP wasn't there, let's say that if I were to switch over to Paint, it's more of like if I put in 1 volt and I get output of 5 volts, then my gain is equal to the V out over V in. And so that's going to be the 5 over 1 volt. And I'll get you your 5 volts per volt. But if somehow whatever I added, whatever I did to like amplify it, maybe I added some kind of operational amplifier which multiplies the gain times something. And then like I just cascade that system here. I just add the system in, and now I'm not outputting 5, I'm like outputting 25. So it pretty much was this original thing but times 5, so 5G. And then your K would be the 5 because you have your original system that through all the S's and like resistances and impedances somehow got you a V out of 5 for a V in of 1. Somehow you included a multiplier which multiplied your gain, and then that's the K. It's a constant. It's a constant that you're able to pull out of your gain. And so maybe it's like 2.314 or 5.786 or whatever. It's like it's the it's just like the form of K times N of S over D of S. Do y'all remember doing problems like that where you'd find your K?
Oh yeah, K
Yeah,
constant.
it's exactly like that. And so it's just the value that you can pull out where you'll have S squared in the numerator and S squared in the denominator or something. And there's no numbers in front of it. And so that's kind of like the KBP.
Oh, okay, makes sense.
Well, I think that's all for me, unless y'all have any questions.
Well, would you mind uploading this document too, like, or is it you're not allowed to do that?
Yeah, I can upload.
Okay, sounds good. That's pretty much on me for questions.
Awesome. Well, I hope y'all have a great night. Good luck on test day on Friday. And if y'all have any questions, just shoot me a message on Discord.
Thank you. Take care.
No problem. You
Yep.
too.
Thanks.
No problem.